Hello, 7th graders. Mr. LaBeouf here, presenting you with what is one of the biggies of middle school math. I believe I've introduced this to you in 6th grade. I generally don't in 5th grade, but introduce it in 6th grade. Then it is an official big part of 7th grade math. Most of Chapter 4 in our textbook is based on this truth. Some vocabulary words. We have ratios, two equal ratios. You can think of ratios, if you'd like, as fractions. They are pretty much the same. Of course, we've used the concept of a ratio to define rational numbers. Rational numbers are numbers which are ratios of integers. Another way to think of rational numbers is they are fractions and negative fractions. So once again, you see that strong connection between ratios and fractions, and it's not probably a bad idea to simply think of them as fractions, but the tradition in middle school math is to talk about equal ratios. And the truth, the big truth here is that if you have two equal ratios, as I've identified up here, A over B equal to C over D, it is automatically true that their diagonal cross products are equal. Now, that's a mouthful. That's why we have the symbolism of math. And this truth holds for all real numbers. And real numbers are all the numbers that you're familiar with: integers, fractions, negative fractions, and also irrational numbers, which, like the square root of 2 and pi, which you haven't done much with yet. But this is true for all real numbers. As long as b and d are not 0, you can never have 0 in the denominator. Let me do something with this red marker that might be helpful in getting you comfortable with this notion of diagonal cross products. So we have these two equal ratios or two equal fractions. The product of A and D, A times D, will always be equal to the product of B and C, which is what this says. Notice the double arrow. The double arrow means that if the left side is true, the right side is true. If the right side is true, the left side is true. They are equivalent statements. I want you to develop an instant reaction to the two equal ratios and know that you can always rewrite that equation, this one here, as that. They are equivalent equations. I can't emphasize that enough. In math, sometimes it's important to develop the understanding of something so well that you just do it instantly. Now, we're going to think about this a lot right now, but in the future, because you've seen exactly why this is true, and we've talked about it so extensively, in the future, when you have a problem to solve, you'll just automatically do it. Like, you don't think about why 9 times 7 is 63 anymore, because you've internalized it. It's become part of your long-term math memory. I want this to become part of your long-term math memory beginning today. First, let's notice what we're not doing. We are not multiplying two fractions. To multiply two fractions, of course, is the easiest thing we do in middle school math. We simply multiply across the top and bottom. The product of A over B and C over D is, of course, AC over BD, but that's not what we're doing here. We are being told that the two ratios or fractions are equal. And then we have this equivalent statement. Let me introduce a vocabulary word. In the middle school math world, when you have two equal ratios like that, or two equal fractions, it is known as a proportion. It is an equation, but it's a special kind of equation known as a proportion, and that proportion can be rewritten as this equation. And that's the main message. That's what I want you to take away from all of this. The next thing I want to talk about is, why is it true? There's a proof of it, a very simple proof that depends on something more basic, something that you've already learned, known as equivalent fractions. And this is how mathematics works. We make definitions and basic assumptions, and then from those we build the structure of math. So if you can accept for now the basic assumption of the equivalent fraction, if you don't remember what that is, you'll see in a moment, we're going to easily prove this truth about the diagonal cross products of a proportion being equal. The truth about equivalent fractions allows us to add and subtract fractions with different denominators. Without that truth, we wouldn't be able to add and subtract fractions. Another thing that equivalent fractions allows us to do is to compare fractions. Some fractions we're not sure which is bigger, which is smaller. How do we compare them? We give them a common denominator, and then it's simple, right? Right here we have two fractions or ratios with different denominators. Let's give them the same denominator. What if you were going to add these two fractions? What would your common denominator be? Of course, it would be b times d. So let's give these two fractions a common denominator. We're going to multiply the top and bottom of this one by d. Now it's still the same fraction, right? AD over BD is the same point on the number line as A over D. And what are we going to do with C over D? We're going to multiply the top and bottom of it by B, by the other denominator, just like when we're adding or subtracting. All right? So it's important to realize that the two fractions that are there now, black and red ink, are the same as the original fractions that were there in just black. Okay? But look at the two denominators. They are now the same. What is the only way that these two fractions with the denominator of BD can be equal? Think about it. They have the same denominator. What's the only way they can be equal? If the numerators are equal, right? If you've got 7 as your two denominators, right? The only way that these two, if we're going to make fractions out of them, the numerators have to be the same. I can't have a 3 here and a 4 here. They wouldn't be the same. So that's it. That's the proof. Because look at what we have here. We have AD and BC. So there's the double arrow. This numerator and that numerator have to be the same. AD must equal BC, just because of the more basic truth about equivalent fractions. So let's now look at a few examples. We used equivalent fractions to prove the truth about proportions, to prove the truth about the diagonal cross products of two equal ratios being the same. Here's an equivalent fractions problem that any fifth grader can easily solve, and usually even in fourth grade this is introduced. Now, obviously that x is 6, right? Because to go from 3 to 9, you multiply by 3, so you have to multiply the numerator, the 2 by 3, to get a number here that will make this fraction equal to that one. So this x here is 6. Easy. But let me show you this. Let me show you how the diagonal cross product truth can can help us in this area. We don't really need it here, but we're going to need it in the future. So that equation, which is known as a proportion, is equivalent to this equation. 3 times x, that's one of the diagonal cross products. 3 times x has to be equal. If those two fractions are equal, and we were told they were equal, that's how I presented it to you, that they're equal, the 3 times x has to be equal to 2 times 9. 3 times x is 18. Divide each side by 3 and get x equals 6. Is that a lot of extra work for solving an easy 4th grade problem? Yes, it is, but it's worthwhile. Trust me. I've seen this movie before. I know some of the things that are going to happen later. And it is crucial that when you are given 2 equal fractions or 2 equal ratios known as a proportion, you automatically know that you can rewrite that equation by setting the 2 diagonal cross products equal. Right? 3 times x must equal 2 times x. Let's look at a slightly harder problem. This problem you will most likely not see a 4th grader have to deal with. The 4th grader would be stuck. The 4th grader might realize that x has to be a little more than 6. 4th, 5th graders could reason that way. 4th and 5th graders are not typically introduced to or responsible for something known as a complex fraction. When we first learn about fractions, the numerator and denominator are both whole numbers. 2/3, 9/10, 5/4, right? As we get into 7th grade, as you know, when we learn about rational numbers, we sort of replace that with the numerator and denominator being integers. So -5/3. And we know that that's the same as -5/3. -5/3. And we know that's the same as 5/3. But the complex fraction is a fraction that contains one or more fractions. Either the numerator, denominator, or both are fractions. And that's why this is not a 4th grade problem, because that x is not a whole number. It's a fraction. Now, I'm going to solve this problem 2 ways, and then I'm going to circle back to the definition of the proportion that I gave you with the letters. All right. First thing I'm going to do here is to take my own advice and automatically rewrite this equation as 3x equals 20. That's right. Automatic. 2 equal ratios, 2 equal fractions. The diagonal cross products. Product means multiply. Must be equal. So if 2/3 equals x over 10, I have running out of a little room here. I'd like to put that over here, but I'm going to put it down here. 3 times x, this time, equals 20. Remember last time it was 18, so we got x was 6. This time 3x equals 20. So what's x? Divide each side by 3. And x is 20/3, which is correct. That's the answer. That's what the x has to be in order for the 2 fractions to be equal, which we were told they were. So we had to come up with that x being 20/3. Of course, 20/3 is 6 2/3. Remember I said maybe the 4th grader would know the x had to be more than 6, right? Well, it's actually 6 2/3. So we end up with this complex fraction. Complex because it contains this fraction here in the numerator. If either the numerator, denominator, or both are fractions or decimals, of course decimals are also fractions, then the fraction is known as complex. And you'll become very comfortable with complex fractions. As you may remember from 6th grade, I think I presented this to you, and we'll do it again, probably this year if I remember to. When we're dealing with percents, not all percents are whole numbers. Whole number percent. Like 25%, 50%. Now those are not whole numbers. 50% is the fraction of 1/2, but the 50 is a whole number. 50%, that's what I call a whole number percent. But can you have 2.5%? Yes, 2.5%. Can you have 1/4%? Yes. That very notion that there are non-whole number percents, and they're out there in the world all the time. Just walk into a bank and look at interest rates. They're not always whole number percents. You might have to pay 3.5% for a loan. Or if you put your money in the savings account, nowadays interest rates are very low. They might pay you 0.1% interest on your money in the savings account. So there are definitely non-whole number percents. So that means there has to be complex fractions, right? Because let's say 3.5%. What does that mean? Well, it means 3.5 over 100. That's a complex fraction because that 3.5 is not a whole number. Now we can convert that to a simple fraction, which is really not part of what I wanted to do now, but sometimes I get carried away. We could convert this to a simple fraction by many ways, but one way might be to multiply the top and bottom by 10. Then we have 35 over 1,000. And again, notice that all-important notion of the equivalent fraction is there as well. Here's the same problem. Now, I do want you to automatically know that 3x equals 20 and instantly get to x is 6 2/3, like we just saw. But I want to show you another way that is, and I'm not trying to confuse you, you're going to develop mastery here through practice, homework, quizzes, and so on. And the way I approach things, as many different ways that I can explain things to you, the better chance you have of achieving that long-term mastery. Everyone's brain works a little bit differently. So here's another approach. Remember the 4th grade problem, when that was a 9. We realized that 3 times 3 is 9, so we did 2 times 3 to get the x is 6, right? Well, there's no whole number to multiply 3 by to get 10. A fancy way of saying that is 10 is not a multiple of 3, 3 is not a factor of 10, but there is a number you can multiply 3 by to get 10. Now, whenever I present that question to students, a lot of times I get students trying to figure out the mixed number. What mixed number do I multiply 3 by to get 10? Students immediately know it's between 3 and 4, and they can here, a lot of you could come up with it's 3 1/3, but I actually don't want you to think 3 1/3. Here's what I want you to think. What is the number you multiply 3 by to get 10? It is 10/3. Okay? Now, this pattern always works. The pattern is the number you multiply 3 by to get 10 is 10 over 3. That works no matter what the numbers are, as long as this number here is not 0. Okay? It always works. Let's look at it from the point of view of algebra. The question, what do you multiply 3 by to get 10, is reflected in this equation, 3a equals 10. What's a? Well, you've been taught to divide each side by 3, right? The a is 10/3. That's the number you multiply 3 by to get 10. Very simple. Simple. Now, if we multiply the denominator of this fraction by 10/3, of course, we have to multiply the numerator by 10/3. What's 2 times 10/3? It's the exact same 20/3 that we got the other way, remember? Two times 10/3 is 20/3. When we used diagonal cross products to solve this, we had 3x equals 20, right? 3 times x equals 2 times 10. We divided each side by 3 and got x equals 20/3. Well, that's exactly what you get if you just think about equivalent fractions here. You see, the proportion and the diagonal cross products that always go along with the proportion are intimately bound up with equivalent fractions. It's just another way of looking at equivalent fractions. So I'm going to go back now to all the letters and do what I just did here, but in general terms. Realistically, when you're dealing with a proportion as a student, how many numbers are in the proportion? How many numbers are there that are making up the two equal ratios or two equal fractions? There are 4. Well, you're going to know 3 and you have to find the 4th, you know? And just what I like to do is identify the unknown number by an x, and that's a tradition in math, by the way. It's not just me. This tradition is not always followed in the middle school textbooks, but there's a pretty strong tradition that the letters early in the alphabet, A, B, C, D, are numbers that we know. We assume that they're numbers that we know. And the letters at the end, X, Y, Z, are unknown numbers. And I'd like to put that unknown number in that top right position. It could actually go anywhere, but I'm going to put it there. So we're trying to find X. Well, we could use, of course, and I want you to use, the all-important truth about proportions and their diagonal cross products being equal. So b times x must be equal to a times d. And the only difference here is that before this was a c. When we were just looking at things in general, we weren't trying to find out what one of them was. That was a c. So we had a times d being equal to b times c. Now we've replaced the c with an x. It's the unknown. So what is x? How do we solve for x over here? Well, we divide each side by b, and we get x is equal to AD over b. Okay. Now let's do it the other way. Equivalent fractions. And the two ways are really the same. The question is, what do you multiply b by to get d? Well, you know, if you were comfortable with what do you multiply 3 by to get 10, and it ended up being 10/3, this is the same, right? The number that you multiply b by to get d, think about it, what would it be? D over b, right? D over b. Let's look at it algebraically. Let me use the letter Q. I'm kind of running out of letters. You know, I got an X, A, B, C. So let me use Q. All right? Q is an unknown. The question is, what this equation says, Q is the unknown. What do we multiply B by to get D? Well, it's Q. B times Q is D, according to this equation. But what is the Q? Divide each side by B, right? And that number, that Q that you multiply B by to get D is D over B. It's this over the B, right? It's just like the 10/3 from before. Now, to keep the two fractions equivalent, we have to multiply the top and bottom by the same number. If we multiply by d over b on the bottom, we have to multiply by d over b on the top, and voila! That's French for there it is. Oop, there it is. A times d over b. What is that? Well, it's AD over b, right? This A can be thought of as A over 1. Multiplying A by D over B is AD over B. So there it is. A little complex? Well, let's go back, review, and give maybe one more example. We'll see. I've got my double arrow going up and down here because I'm trying to coordinate you seeing things, and if I'm way off to the side, the sound might not be good. But anyway, we've got A over D equaling C over D, two equal ratios known as a proportion. Ratios are basically fractions. If this is true, this is automatically true. A times D equals B times C. The diagonal cross products are equal. So, do you want to get a little crazy? Would you like to get crazy? All right. Let's jump right to Algebra 1. The problem that I'm going to put on the board next appears at the beginning of the Algebra 1 textbook. But a lot of times in math, what you realize is, if you've been doing this for now more than 21 years, you realize that there's nothing new under the sun. There are only a few basic ideas in math, and they just keep getting applied. So, watch this. I thought about, just now while you were waiting for me, I thought about whether I should make this work out nicely. In other words, whether the x should come out to be a whole number. Whether I should rig the equation so that the x came out to be a whole number. I decided not to rig it. Now it might, the x might come out to be a whole number, but I doubt it. Actually, the Algebra 1 problems that I talked about get a little bit more complicated than this, but not much. I decided not to go full Algebra 1, just a little bit toward that. The full Algebra 1 would have been if there had been some x over here in this numerator. We've actually looked at equations with variables on both sides, but that's pretty advanced for 7th grade, so I opted for the somewhat simpler one. All right. We have two equal fractions. Automatically, their diagonal cross products are equal. So, something's going to equal 35. 5 times 7. What's going to equal 35? 3 times 2x plus 1. But here's something that comes up over and over again, beginning in 7th grade, throughout the rest of your lives in math. In order to multiply 2x plus 1 by 3, we've got to multiply that entire 2x plus 1 by 3. So we have to insert parentheses and use the what? That's right, the distributive property. We have to use the distributive property here. Okay, just think of it this way. If we said that 3 times 2x plus 1 was 6x plus 1, that's wrong, because we haven't multiplied the 3 by the entire 2x plus 1. Insert the parentheses, use the distributive property. 5 times 7, 35, of course. That's one of the diagonal cross products. The other diagonal cross product is 3 times 2x plus 1. Automatic response, right? Go back to that. A over B equals C over D. Automatically the diagonal cross products. I can't tell you how important, I can't tell you enough how important and valuable that will be going forward. Apply the distributive property. Now, one option here would have been to divide each side by 3, but 35 is not a multiple of 3, so let's apply the distributive property. 6x plus 3 equals 35. And I can tell at this point that the x is not a whole number. Okay? There are several steps to this equation. The first is to simply set the diagonal cross products equal. We received two equal fractions, we automatically know what we can do. Rewriting an equivalent equation. Both of these are equations. This one here is called a proportion, but you can rewrite the proportion as this equivalent equation, which you know how to solve. Of course, we're going to subtract 3 from each side next and get 6x equals 32, right? This had to be 32. I subtracted 3 from each side, and now we finish by dividing each side by 6. Let's immediately express it as 16/3, right? Now, we've set new ground rules. You don't have to convert to a mixed number, but the x would be, what, 5 1/3 if you did that. So either way. Let me close with this observation, this reminder. It's a reminder. What does it mean to solve an equation, whether it's like down here or whether it's the original proportion, which is an equation? What does it mean to solve an equation? It means to find the number you can put where the letter is to get a true statement. And in theory, you should always prove that what you think is the solution by getting that true statement. We don't always have the time to do it, but let's take that 16/3 and put it where the x is and see what happens. Okay? Now, we're going to end up with, I think, a complex fraction, right? This numerator here, the 2x plus 1, is not going to be a whole number because you cannot have thirds equal to sevenths. 3 is not a factor of 7. 7 is not a multiple of 3. So you cannot have thirds equal to sevenths with just whole numbers. So you have to be willing to accept that complex fraction. So let's see what happens putting the 16/3 where the x is. Well, the numerator over there is 2x plus 1. We're saying that x equals 16/3, so 2x is 32/3, right? 32/3. 2 times 16/3, 32/3, that's easy. Plus 1. Well, let's stay away. Let me introduce you now to another thing that smooths things out sometimes. Rather than converting that 32/3 to a mixed number, then adding 1, how about if we just add 3/3 to the 32/3, right? How about if we just think of this 1 as 3/3? It is 3/3. So now what we get is 35/3 is the numerator. When the x is 16/3, we get 35/3 for our numerator. Our denominator is 7. No, there's a complex fraction. 35/3 over 7. How can we simplify it? How can we make it a normal fraction, simple fraction? Well, what does it mean to divide by 7? Think of it as 35/3 divided by 7. Isn't that the same as multiplying by 1/7? Dividing by 7 is the same as multiplying by 1/7. So this is 35/3 times 1/7. Right? And that's 35 over 21. I know that this has been long. There's a lot going on in this video. Pause it when necessary. Re-watch it if necessary, as many times as necessary. I don't always know where things are going to lead. I thought I was introducing a very simple concept, but everything in math relates to each other. If you're going to explore a topic, you have to get into many other things. Sometimes you're not even sure that are going to come up, but they do. But how about this question? What do you suppose 35 over 21 simplifies to? This is the ta-da moment, ladies and gentlemen. All right, we used diagonal cross products to solve for x here. We said that 3 times 2x plus 1 has to be the same as 5 times 7, and we got x equals 16/3 using skills that you have. All right? We put the 16/3 where the x is over here, and there's some math going on there. Here's a interesting thing. Sometimes, we solve an equation and we get x equals a number. And then I've told you that in theory, we should always put that number where the x is to see if we get a true statement. Or checking the solution. Sometimes that's harder than getting the solution. Often it is harder to prove that the solution is correct than it is to get to it. Okay? Well, do you see what 35 over 21 simplifies to? You can divide the top and bottom there by 7, right? 5/3. Right? Which is right there. Bam! Mic drop. Bye-bye.